Good morning, mathematicians. How are we all doing today? Back to it. I realized I was just getting this document set up and I realized, indeed, I did miss a very obvious thing here. Or not very obvious, but, well, I'll explain in a second. Just getting this document set up and I realized, I hope everyone's doing well, though. And yeah, also, as you can see, office hours are back to being a little bit earlier. I don't know if they'll always be at this time. You know, I'm never consistent there, but let's see, 7:53. I don't want to do a long office hour, but I'll try to not do a short one today for you guys. But I don't know, maybe these office hours are less popular now anyways. I think in terms of views, it's about consistent. I get the same number of views. But how entertained are you guys by this? I always do wonder. Okay. Yeah, so the whole issue, I was confused about the claim about this commuting diagram, but I had the wrong map in mind. I thought it was just inclusion, but we are actually taking, this map. We are doing proper class field theory now, I think. Yeah, I guess this counts. I guess this is that. I was thinking about maybe taking a break at the end of this chapter and doing some regular office hours, or doing some spectral sequences. But we'll see. We shall see. So let's talk about the invariant map. Had we actually started talking about this last time? I don't think so. So, we've got an unramified extension. We've got our Galois group. And we know that H2 and H3 of this are 0. I think we saw that last time. So taking cohomology of this short exact sequence gives us an isomorphism here. This does seem familiar. I think we have talked about this. Maybe I'm wrong. So the groups. Right. We did cover this right at the end, but this is where I got confused. These groups are torsion and uniquely divisible. What does that even mean? Yeah, divisible group, but what is uniquely divisible? There's a unique largest divisible subgroup. Yeah, I don't know. What is it? What is uniquely divisible group? A uniquely divisible group is an abelian group where for every positive integer... Oh, there's a unique thing. Oh. I really should have been able to parse that. Okay. Sure. They're torsion, but they're uniquely divisible, so they're 0. Okay. Therefore, if we take the cohomology of this sequence, we then get these isomorphisms. And why is H1 the continuous Homs? Recall from when? The section on profinite groups? Certainly. I feel that way often, Vishal. I feel that way often about a lot of things. But right now I feel calm. And on the verge of feeling caffeinated. Okay, let's go cohomology of profinite groups. Let's remind ourselves why this is true. Because, I mean, you would think that would be H0. I would think that would have been H0. But perhaps not. Oh, no. So, and now we're back to homological algebra. Wait a second. What happened? I mean, this was the only section we talked about continuous cochains, right? So each one of a trivial action is always Hom? Oh, because crossed homomorphisms, right? Thank you, Arad. We were missing you yesterday when I was making stupid mistakes. I did eventually recognize the stupidity of my mistakes this morning, but I'm glad that you're here now to help more immediately. And we even say here trivial G actions, right? Okay. Trivial G actions, right? So then we've got isomorphisms. We saw that one. Right, trivial G action. Okay. G has a canonical topological generator. That's because we're an unramified extension. What's math without some stupid mistakes? Exactly. One could say that essentially that's all math is, the long series of stupid mistakes. And then there's like a tiny sprinkle of being correct here and there. Okay. Yeah, I'm starting to see a friend of mine said that if we read the chapter 1 of this book, the Lubin-Tate theory, it's all much more computable, whereas this is maybe nicer for proofs. And this definitely seems like, there's a bit of this wouldn't. Maybe it's not so bad. Although if I'm going left to right, like computing the inverse of delta, that seems like it's maybe a little obscure. Okay, so we call this the invariant map. And then we have this claim that it's compatible with extensions. I guess that makes... The only thing that is maybe questionable to me is maybe here, like, I could believe the ORD is compatible and that this is compatible. You know nothing about math. Well, you must know something. But you've been tuning into these for some reason. Well, I'm glad that you're still enjoying it nonetheless. To the uninitiated, these notes look like a conduit for dark magic. Well, let me tell you, these notes look like a conduit for dark magic to the initiated as well. And some may even say that class field theory is dark magic. So, you know, your intuitions are correct here. Your intuitions are absolutely correct here. I'm glad you're enjoying them anyways. Honestly, a big reason I got into math was just I wanted an excuse to write these freaky symbols. You can mix proofs, use cohomology to prove reciprocity, and then formal groups to prove the existence. Oh, good to know. Good to know. Okay. But you're skewed towards Lubin-Tate stuff because it comes up in homotopy theory. Oh. I do remember there was this, I understood nothing. I learned nothing from it because I was too much of a young little baby. But I was at the Arizona Winter School, which was about the intersection of arithmetic and homotopy theory, and Jacob Lurie was there, and he gave one of the series of lectures, and I remember that there was stuff going on about formal groups and Lubin-Tate stuff, but it was totally beyond me at that time. Yeah, I've seen the words Lubin-Tate come up in some local Langland stuff, but again, never really understood it. Maybe I should go back and read chapter 1 of this book, and then go read the generalization of Lubin-Tate stuff to local Langlands. Okay, but let's take a look here. So we have our invariant map, and the invariant map should be compatible with inflation. Because all the maps in the definition of inv are compatible with inf. Okay. I guess I feel a little guilty for us not sitting down and writing it out. What's local Langlands? Well, local Langlands is, in some sense, a generalization of what we're looking at now. Class field theory. What we're looking at now is essentially a relationship between representations of GL1 QP, I would say, and I guess maybe this is one way to phrase it, and representations of the abelianization of its Galois group. That's basically what we're looking at. And local Langlands more generally seeks to turn this one into an N in an effort to be able to remove this abelian. In short, that's the quickest description I can give you for local Langlands. But if you want a more detailed description, you should find Stephen Kudla's article on the local Langlands conjecture for GLN, because that's really insightful. So I'd recommend checking that out. Okay, so it seems like a significant theorem. There exists a unique isomorphism, boom, here, with the property that for every unramified extension of finite degree n over n, or over k, the invariant map induces an isomorphism here. Okay. This is an immediate consequence of the above discussion. Unclear. This is unclear to me. Why would that be true? So L's the smaller field here. So H2, we've got H2 L over K. We've got inv L over K into QZ equal sign QZ H2 K un over K inv K un over K and inflation. Let me go back and look at the conditions of this. Oh, okay. This is not necessarily an isomorphism. Right, this is not necessarily an isomorphism. Speaking of mixing proofs, you can also compute this invariance thing without cohomology, but explicitly as the Brouwer group. Much more concrete and computable. Yeah, I'm very interested in the Brouwer group. Not actually so much for number theoretic reasons, but what I find really interesting about it is that you went from looking like math dork to prison inmate. Well, better watch it then. Better watch it. Calling me a math dork. Now, you know. Now I'll come at you with me and the gang. So, you know, I even got the tats. So. Where was I here though? Yeah, so I guess maybe then maybe this has to do with the inflation map. Is the inflation map in this case? I know we have some theorems about it just becoming well, no, we've got theorems about the composition of co-restriction and restriction being the index of some multiplication by the index of some subgroup. Is there a similar thing here that we use to get this? Yeah, maybe if I scroll up a little. Is there possibly something we saw yesterday about this? Hello, Nightbook. This seems interesting, but you don't know what you're looking at. Yeah, so we are a little deep in this saga to give a quick explanation, but okay, I'll tell you a little bit. We're trying to understand something called class field theory and Galois cohomology. So, and forgive me, I don't know your background, so maybe these words I'm going to start with are already too far beyond. But the point is that we want to understand field extensions. So an extension of the field of rational numbers. So this is just some bigger field that contains the rational numbers. And one way to study that is there's a bunch of related fields called the p-adic numbers. And so the idea is if we have one of these extensions, it actually tells you how to build one of these extensions. And our hope is that we can pass information back and forth between these things. And so one way that we study field extensions, I mean, the big thing that Galois did, which allowed us to prove these crazy things like the insolvability of the quintic, was he looked at, Galois, so-called Galois groups attached to these field extensions. And in turn, one could pass information back and forth between the fields and the structure of these so-called Galois groups. Okay, so you know a little bit about fields and groups, so hopefully what I just said to you at least makes some sense at like a high level. There's some way that we can use these special groups of symmetries of a field to study structures of the structure of fields, and this allows us to talk about things like solvability of polynomials and whatnot. But now we're going to jump up a level or two of abstraction. So you maybe have heard about representations and representation theory. So this is when we have a group act on some sort of, representation is normally a vector space, but we can have a group act on some sort of thing. Chemist learned about functors a few weeks ago. Well, hell yeah, we love to see that. We love to see chemists and functors coming together. So basically what this means, for each element of the group, it tells you a map of your underlying space, a way to push around these elements. And there's particularly nice ones that are maybe so a slight generalization of the idea of when X is a vector space of a representation, which I won't go into the definition of, but it's called a module. And so we can have our groups acting on a module, and that tells us sort of information. So in particular, what's an example of this happening? Well, like your Galois group of some field extension acts, say, on the field itself. This is an example of a module action. And it also will act on, say, the group of non-zero elements of the field in a way that respects, the multiplicative structure. And now, for a higher level of spiciness, there are these things called cohomology groups, which are even more different groups yet. So these are the things, the HRGL. So here, the L is a field, LX is the non-zero elements, and HR, this is called the group cohomology with respect to the Galois group. And I'm writing Q everywhere here, but right now in this section of the book, we're thinking about QP. And so we get one of these for every R in the integers, and these are just a bunch of groups which sort of store information that's going on about these things. By the way, I have another series. I have a sort of series of pre-recorded videos on my channel I've been releasing, and I think not this Friday, but the Friday after that, I'll release a new one where I talk about the theory of extensions of groups and semi-direct products, and I talk about how group cohomology ties in there. But in this book, we're considering how number theoretic information that can be captured by these so-called cohomology groups. And what's maybe a good example of a theorem I can show you here that highlights this. Well, I think we're close to I think we're close to being able to state some things. Maybe if I scroll down a little bit, there'll be something. Right. So there's this thing called the local. There's this thing called the local Artin map. So that is basically this map here. So as an example, it turns out that this Galois group, or rather, should it be the abelianization maybe? Give me 1 second here. Yeah, no, it's just G in this case. I don't know what special cases we have, but okay. I mean, from this example, we can do some cohomology nonsense, and one of the takeaways is that we know that in a certain case, our Galois group, which, in general, it might be hard to determine that structure, but it turns out we get this general theorem. So in this wide variety of cases, it tells us that our Galois group looks like this. So it's our smaller field, X cross, modulo some subgroup. So if you already know your field and the extension and you're having trouble computing the Galois group, this could be some very useful information that you get out of it. So that's just one example. I mean, this is a large and powerful theory. So yeah, if you heard of all those zeta function shenanigans, their definition also relies on Galois representations, and they're very important. Indeed, Arad, indeed. But now let us return to the task at hand, and why is this immediate from the above discussion? That is a question I have. This should have something to do with inflation, right? So if I type inf and go back, oh, is there something here? Oh no, that's cohomology ramified. I want to go back. Gotta pour myself some more coffee. K being infinite, ramified extension. No. Most of the theory concerning cohomology groups continues. Sure, okay. Let's go back further. Could it be something to do with, right, the inflation map realizes this as a direct limit of groups through the open normals. Is there something going on there, maybe? Is there possibly something going on here? Probably drew my limit pointing in the wrong direction. I'm just gonna write that down and remind myself. Inflation, I'm always inflation. We're looking for something to do with the index, though. And I only remember seeing this for the composition of co-restriction and restriction. We've got cup product compatibility. Oh, is there something there? No. Yeah. Well, I don't know. Do we just believe it and move on? I feel like I'm not really learning the subject. I'm getting the main ideas, I guess. Let's go back to where we were. It's around here, 108, page 108, I guess. I really should be doing homework in between streams. I know I say this every episode, but I'm not going to do it. I don't have time. Maybe I have time. I don't know. I elect to spend my time on other things. Immediate consequence of the above discussion. Let's look over it one last time. And see. Maybe something about here. Maybe something about this part, right? F goes to F sigma. F goes to F sigma. Maybe because inflation factors through some restriction map? Does it? I feel like I need to make a big list. Actually, I was on a plane recently. Oh, I don't have my notebook here. And I did actually do a little homework. I did go back and prove a couple things a little more carefully in the notes. And I did make a list of theorems, but I feel like I need to go through this again and like write out a list of some of the main theorems. This is the important this is exactly why you do homework, because then you end up using theorems in exercises, and then that's how you remember the theorems that are in your toolkit. So maybe you're right, Arad. Maybe you're right. But well, I'm just not sure how to see it right now. So I guess we'll move on. Immediate consequence. It's bugging me. I mean, something here. The order map. Maybe it has something to do with the order map. Ord L. Right? There we send an element to its order. So yeah, something going on there, because like the maximum order of any element is L over K is the index. I mean, it's starting to like be vaguely believable to me, but I still don't quite get it. These are some really dense notes. Yes, Bayu, this is true. Any idea why mathematics feels like it tries to pare down words to fit as many ideas onto each page as possible? 296. Yeah, I mean, 296, well, I mean, as you can see, right, these notes are very dense. This is certainly not the densest set of notes in the world, but you can see this is already almost a 300-page book. And this is the result of trying to make things somewhat dense or concise. Well, it's there's a bit of a give and take on the part of the author and the reader, right? One might imagine, in an ideal world, that one would have a book that explains every part of the proof extremely carefully, But is this really the ideal? Well, it's probably not the ideal for the author, right? Because someone has to write it. And, I mean, we do make textbooks as a means to try and offer an easier explanation for people trying to learn other than just reading directly from the literature. And sometimes it's just as simple as, well, having a bunch of results collected in one place helps do that, but also, trying to offer some exposition and examples to clarify things. But, there's only so many hours in the day that one can spend writing textbooks, and one also needs to make a career out of doing mathematics, and one who is motivated and talented enough to write a textbook on a subject probably just has a desire to continue publishing research papers as well. One also must think about the reader. The struggle, I think, is an important part of the learning process. So I don't think you would want every single detail. Well, of course, secretly, we all do want every single detail laid out for us. But I don't know that that's the best. And so the difficult question comes in, where is the fine line between too much detail and not enough? And there's no objective answer to this. So, yeah, I don't know. It is tricky. So why are these notes this dense? Well, probably someone, Milne didn't feel like writing 1,000 pages. And to be honest, I would not feel like reading 1,000 pages. So 300 is the rough compromise between Milne and the readers of what is maybe an acceptable amount of detail. Yeah. Yeah, exactly. Chemistry papers would seem the same. I'm sure it's the same across all disciplines. Okay, suppose we have a finite extension of degree n. We've got the largest unramified extensions of both of these. Then we have, the restriction map commutes with just multiplication by n. Wait, multiplication by n? Is that what that means? Multiplication by n. Isn't that just 0 if we're doing mod integers? Or is this like plus n mod? I don't know. Let's look at the proof. The largest unramified extension of a local field is obtained by adjoining all the mth roots of unity for m not divisible by the residue characteristic. Therefore, this is true. Sure. I believe it. You personally feel better when you understand something this way. When you understand something which way? Reading it at a high level? Or reading all the gritty details. A fraction times n may not be an integer. Oh, of course, I'm such a silly little boy. Such a silly little boy. I hope you guys are entertained by me. Part of the time. Okay, let's look through this proof. God, this is a long proof. It's not that long. Okay, I think we'll look at this and then probably wrap up for today. The largest unramified extension. Yeah, here we are. So this map should be injective. Right, because we just have this decomposition of fields. Right, I vaguely recall some theorem like this. The map denoted res in 27 is defined by the compatible homomorphisms. Right. Field inclusion and restriction, the restriction map. Okay. We'll introduce some notation to make our lives easier. And then we have the claim that this diagram commutes. I think this would take a little bit of work to prove carefully. But I guess I could be willing to just believe it. Well, I guess I can believe we have these theorems about multiplying by some kind of index, right? So, I guess it's not crazy to me that, like, yeah, here we're taking the unramified extension here, so that should be the unramified index. Yeah. Not totally crazy. And then, yeah, here we have another, same kind of result with that index. Yeah, here E is the ramification index for this extension. F is the residue class degree. I guess I'm willing to believe it. Always got to look at the next sentence, yeah. The first square is obtained from this commutative square. Indeed. There we go. Okay. That's right. No matter how many times I remind other people and myself of this. Yeah. Anyways, okay, so the first square is obtained from this commuting diagram. Great, that makes sense to me. The second square is obtained from the fact that the restriction map commutes with the boundary map, apart from the factor E. The third square is this. I mean, we do have this, but then I guess we multiply through by an E, and that shouldn't affect those maps. The Frobenius elements are determined by the fact that they induce X to XQ and X to XQF respectively on the residue fields. And so restriction is this. And then it's now clear that the square commutes because of this. Yeah. Let me just go up and compare these two squares. How exactly does the E show up? I'm a little off on that. Oh, because I see. I guess he's saying this restriction map. This is restriction to gamma L, but he's comparing this to the restriction map, which, oh yeah, res should be via gamma L as well. Okay, but whatever. I'm happy. I will try to do more homework and do some of the tedious calculations. But I think we'll leave it there for today. We'll come back. This is tomorrow. We'll start back with one of these big theorems, local Larton map. That's a big deal. So, yeah, hope you enjoyed this. I don't want to call it a longer office hour because, it used to be the regular I'd do an hour. over an hour, but what can I say? I'm a busy man. Longer than usual. Anywho, you know the drill. Go prove some stuff and